Hello and welcome to the Deep Dive. I'm your host.
And I'm your expert contributor. It's great to be with you.
So picture this scenario, something I think many of you listening have probably experienced. You ask an AI chatbot, maybe one of the really advanced ones, a complex question, and it comes back with this just brilliant answer, perfectly phrased, insightful, maybe even give you a step-by-step plan.
Right. They're amazing at generating text these days.
Exactly. But then what happens? It just stops. It doesn't actually do anything with that brilliant plan or insight it just gave you.
And that's been a huge hurdle, hasn't it, for years now in AI, that fundamental gap between, knowing something and actually acting on it.
It really has. We get these incredible insights, maybe a strategy, a piece of code, a travel plan.
Yeah.
But then the burden is still completely on us, the humans, to take that information and translate it into real-world action.
It's a major limitation.
But today, we are diving headfirst into a story that has sent, genuine ripples, maybe even shockwaves, through the AI community.
Yeah, this one got a lot of attention.
Because it's about a model that doesn't just feel like another small step, another iteration. It really feels like the start of a whole new chapter. A chapter where AI finally starts moving beyond just talking about things to actually truly doing them.
The Doer AI, as they're calling it?
Precisely. We're talking about Kimi K2, the new open-weight model from a company called Moonshot AI. And listeners, if you're thinking, oh, great, another story about a bigger model with more parameters, I urge you to stick around.
Yeah.
Because Kimi K2, it's more than just numbers. It feels like a statement.
Definitely a statement. It's almost like a manifesto.
Yeah, it's the manifestation of a whole new philosophy, a really significant bet on a profoundly different direction for where artificial intelligence might be heading. Okay, let's unpack this.
It's a very, very ambitious bet. And what's fascinating here is, the architecture is impressive on its own. Kimi K2 is built on what's called a mixture of experts model, or MOE.
Right.
And it boasts this just staggering headline number, 1.04 trillion total parameter.
A trillion. That number still sounds wild.
It is. But here's the kicker, and this is really, really central to our whole discussion today. Despite that immense potential size, it only activates about 32 billion of those parameters for any given task it's performing.
Okay, so only a fraction is actually working at any one time.
A tiny fraction, relatively speaking. Think of it like this. Imagine you have the entire Library of Congress at your disposal. Just this vast, unbelievable ocean of knowledge covering every conceivable subject.
Okay, got it.
But when you have a specific, really intricate question, say, about quantum physics or Renaissance art, you don't need the whole library. You only need to consult with a handful of, world-class specialists from within that library.
Makes sense. You find the experts.
Exactly. Maybe 8 incredibly focused experts are all you need for that specific answer. Kimi K2 works like that. It has this massive scale underneath, but it achieves surgical efficiency by only bringing in the relevant specialists for the job at hand.
That combination.
Yeah.
Massive scale plus surgical efficiency. That sounds incredibly powerful.
It really is.
Sure.
And that combination is right at the heart of what makes Kimi K2 so compelling and, frankly, revolutionary.
But the tech itself, as impressive as that sounds, it seems like it's serving a much deeper purpose here, doesn't it?
Right.
Reading their materials, the Kimi team is incredibly explicit about their vision.
Oh, yeah, they don't mince words.
They state clearly they built this model, quote, to do things, not just talk. They're actively trying to tackle what many people in the AI community are now calling the action gap.
Oh, that phrase again.
That chasm, right.
Yeah.
Between an AI merely suggesting what to do, maybe outlining the steps, and an AI actually autonomously doing it.
Yeah.
They want to move us from these, basically passive chatbots we're used to towards active self-directed agents.
Agents that can take initiative.
Exactly. So this entire deep dive today is dedicated to understanding Kimi K2, this so-called Doer AI, and exploring what it truly means for the future, how we interact with AI, how we develop it, maybe even how we live alongside it.
And that mission, that shift towards doing, it fundamentally changes the whole paradigm, doesn't it? How we even conceive of and build AI intelligence. It stops being just about better conversations or more creative text.
Yeah, it becomes about tangible outcomes,
right.
Real-world results.
Exactly.
So let's start right there with that core philosophy, because it genuinely seems to set Kimi K2 apart from almost everything else we've seen dominating the field. For years now, the main focus, the dominant paradigm in large language models, LLMs, it's been about creating models that can chat effectively, write coherent text, summarize long documents.
Right, processing and generating language based on that huge static pile of human knowledge scraped from the internet.
And the progress there has been phenomenal, undeniably.
Yeah.
But Kimi K2 is built on a completely different foundation, one its creators call open agentic intelligence.
A very deliberate term.
It is. So for someone listening, trying to wrap their head around this fundamental shift, what does open agentic intelligence actually signify for us as users and maybe for the whole AI industry?
It really represents a fundamental departure from the kind of reactive, one-shot AI interactions that we've mostly gotten used to.
What do you mean by one shot?
Well, typically, you give an AI a prompt, right? It
Yeah.
gives you a response. That's one exchange. Then the interaction is basically over. The ball is back in your court to decide what to do next.
Okay.
The action gap you mentioned earlier, that's precisely it. It's the significant chasm between an AI merely saying what to do, maybe giving you instructions, generating a plan, offering advice, and then actually going ahead and executing that plan autonomously.
Right. Bridging that gap.
An agentic AI, by its very design, is built to bridge that chasm. It's conceived not just as a conversationalist or an information source, but as an autonomous digital worker.
A digital worker. That's a strong image.
It is, and it means it's designed to be able to create and refine its own plan, to effectively use a wide array of tools, think APIs, web browsers, code interpreters, to interact dynamically with its environment, whether that's digital or even potentially physical someday.
And it keeps going.
And it doggedly pursues a specific, often complex goal with minimal or sometimes even no human intervention along the way. It moves beyond just answering isolated questions to actively solving multi-step problems in the real or digital world. It acts like a true digital collaborator, or in some cases, maybe even an independent operative.
And what I found particularly compelling reading their technical report is how they explicitly connect this core philosophy to a really profound concept from two giants in the field of reinforcement learning, David Silver and Richard Sutton.
Ah, yes, the era of experience. That's not just a casual mention, is it?
Not at all. It seems absolutely central to Kimi K2's entire reason for being. The core thesis here, as they present it, is that we are rapidly reaching the practical limits of what AI can achieve just by training on static human-generated data. That's what they call the era of human data.
Basically training on the internet as it exists today.
Exactly. The next great leap, according to this philosophy, championed by Silver and Sutton and embraced by the Kimi team, won't come from just finding more static data or building incrementally bigger models trained on that same data. It will come from systems that learn from their own dynamic self-generated experiences. Learning by doing, essentially. Learning by interacting with environments.
And you've hit on such a critical distinction there. It's the profound difference between, let's say, theoretical knowledge and actual practical application.
Like reading versus doing.
Precisely. Imagine someone trying to learn how to ride a bicycle. They could read 1,000 books about it. The physics of balance, pedal mechanics, steering geometry, everything. That's the era of human data.
I'd know everything about bicycles.
They'd be an encyclopedia of cycling theory. But the true capability, the actual ability to ride that bicycle safely and confidently down the street, that only comes from the direct experience of getting on the bike and trying.
Feeling it out.
Feeling the balance, right? Getting that immediate feedback from a slight wobble that you instinctively correct. Maybe even having a minor fall that teaches you about recovery. Or perhaps a scraped knee that tells you very clearly what not to do next time.
The school of hard knocks.
Exactly. That's what builds true ingrained capability. The muscle memory, the intuitive understanding that goes beyond just reciting facts. Kimi K2 is designed from the ground up to get on the bike. Its entire training process, especially in the later crucial post-training stages we'll talk about, is built around simulating these interactions, trying things out, sometimes failing, sometimes succeeding, but most importantly, learning from the direct consequences and feedback of its own actions within dynamic environments.
So it's not just fed data. It generates its own learning experiences.
That dynamic, experiential learning is what truly sets it apart from models primarily trained on just reading static text.
That bicycle analogy really makes it click. It's the difference between knowing about something and truly knowing how to do it. Which brings me to this almost counterintuitive description I saw in their report. They actually call Kimi K2 a reflex-grade model without long thinking.
Yeah, that phrase jumps out, doesn't it?
It does.
Definitely.
Because my initial reaction, and I bet a lot of listeners might feel the same way, was, hang on a second, isn't long thinking or deep, deliberate reasoning exactly what we want in advanced AI? But reading more, that seems to be fundamentally missing their entire point, isn't it? Tell me more about why that's actually a feature, not a bug, for what they're trying to achieve.
It absolutely is a deliberate feature, not some kind of design flaw or limitation. The Kimi team, they weren't setting out to build a digital philosopher, right? An AI that will ponder the meaning of existence or get lost in endless abstract contemplation.
Not its job description.
Not at all. Their goal was very specific. Create a hyper-competent, incredibly reliable workhorse, an AI optimized for practical, autonomous execution of tasks. Think of it this way. If you hire a master craftsman, say, a highly skilled carpenter to build complex custom furniture, or an experienced surgeon to perform a delicate operation,
Okay.
you don't want them pausing halfway through a critical cut or a crucial incision to have an existential crisis or deliberate endlessly on abstract theoretical possibilities, right?
Definitely not. You want them to just do the job.
You want them to possess that ingrained skill, that almost unconscious competence, that reflex-grade capability to measure precisely, cut accurately, assemble perfectly, or operate efficiently time after time after time. Their expertise is so deep, so practiced, that the correct action becomes almost instantaneous, almost reflexive.
So Kimi K2 is designed to be that kind of master craftsman, but for digital tasks,
Yeah.
like coding or data analysis or managing workflows.
Precisely. It's optimized for the rapid, reliable, and crucially autonomous execution of complex workflows. For tasks like, say, planning a multi-city travel itinerary that involves booking flights, finding hotels, arranging local transport across multiple stops.
Things that involve many steps and tools.
Exactly. Or meticulously analyzing a vast, messy data set to extract specific insights and then generate interactive reports. Or even refactoring a large, complex code base to improve its efficiency and maintainability. For those kinds of tasks, you want that relentless bias for action. You want the model to execute a step, immediately interpret the result, and then seamlessly, without hesitation, take the very next logical action.
Without needing constant hand-holding or prompts from a human.
Right. Without getting lost in endless deliberation or requiring you to say, okay, now do the next step. The strategic positioning, this focus on being the definitive doer, and the deliberate engineering choices made to achieve that reflex-grade execution that really sets the stage for all the architectural and training decisions we're about to dive into. It's all about efficiency and effectiveness in the real world, not just abstract intelligence.
All right, that vision is incredibly clear now, almost tangible. We understand the why, the philosophy, the ambitious goals. Now, let's pop the hood, so to speak, and look at the engineering marvel that actually makes this doer philosophy possible. As we touched on briefly, Kimi K2 is a mixture of experts, or MOE model. For our listeners who might not be intimately familiar with that specific term, can you break down what that architectural choice actually means in practical terms? And why is it so critical for achieving the kind of performance Kimi K2 demonstrates?
Okay, let's unpack this. Absolutely. So to really understand MOE, let's maybe expand on that Library of Congress analogy we used earlier. Imagine you're tasked with building a truly comprehensive problem-solving team. A team capable of tackling basically any issue in the world, from, I don't know, astrophysics and quantum mechanics to ancient Greek literature and advanced software engineering.
Okay, a team of universal experts.
Right. Now, a traditional dense AI model, the kind that was dominant before MOE became more popular, is kind of analogous to hiring one single, incredibly brilliant individual and then trying to force that one person to become a world-class expert in absolutely everything simultaneously. Physics, poetry, finance, coding, history, and you name it.
That sounds impossible and incredibly inefficient.
It's fundamentally inefficient, if not impossible. They'd be spread incredibly thin, unlikely to achieve true deep expertise in any single area. Their brain, metaphorically speaking, would be trying to compute everything all the time for every query, leading to massive computational bottlenecks.
Right. It's like trying to store that entire Library of Congress inside one person's head and expecting them to recall every single fact instantly and flawlessly for every single question, no matter how irrelevant most of it is.
Exactly that. Now, a MOE model, and specifically Kimi K2, takes a fundamentally different, much smarter approach. It's like, instead of hiring that one impossible generalist, you hire, say, 384 different world-class specialists.
384. That's the specific number for Kimi K2.
That's the number they report, yes. So you have one specialist who is an unparalleled expert in Python programming, another who is a leading global authority on 18th century French literature, another specializing only in quantum field theory, and so on. Kimi K2 specifically has 384 of these distinct expert networks, each effectively specializing in a particular domain of knowledge or a specific type of skill.
Okay, so a huge pool of specialized talent. But how does it know which one to use?
Ugh, that's the elegant part. When a new task or prompt comes in, let's say, debug this complex Python script that interacts with the financial database, there's a component called a smart router, often referred to as a gating network. This router instantly analyzes the incoming task. It looks at the problem and intelligently directs it only to the most relevant specialists from that pool of 384.
So it figures out who's needed.
Exactly. It might say, okay, for this specific Python database problem, we definitely don't need the French literature expert or the astrophysicist right now. We need the Python expert, the algorithm expert, maybe the SQL database expert, and perhaps 5 others who are highly relevant to coding, data structures, and financial APIs.
And it activates only those few.
Precisely. It only activates about 8 specialists on average, which corresponds to roughly those 32.6 billion active parameters we mentioned earlier, just for that specific part of the task. The other 376 experts, they don't even get involved. They essentially sit back, conserving computational energy and valuable resources.
Wow. So Kimi K2 gets the immense benefit of possessing this vast underlying knowledge, all 1.04 trillion parameters worth, without the crippling computational cost of trying to use all of it all at once for every single problem.
It's genuinely efficient intelligence. Scale combined with focus.
And this specific choice making it so sparse, right? Having 384 total experts, but only activating around 8 at any given moment. That wasn't just like an educated guess or a random design choice, was it? The report mentioned something specific about how they arrived at this structure.
No, it was very data-driven. The technical report for Kimi K2 details something they meticulously discovered through experimentation, something they call a sparsity scaling law.
A sparsity scaling law. Okay, what does that mean?
Basically, they ran extensive experiments and found something quite remarkable. If you keep the number of active experts the same for any given task, let's say you always use 8 specialists, they found that consistently increasing the total number of available specialists in the overall pool, just making the bench deeper, invariably makes the model perform better overall.
Really? Even if you're still only using 8?
Even if you're still only activating 8, a model with a higher sparsity ratio, meaning it has a larger overall pool of specialized knowledge to draw from, even if only a few are active, seems to learn more efficiently and effectively during its training phase, and then performs better when it's actually put to work.
That's fascinating. So more available options lead to better specific choices.
It seems so. And this crucial empirical finding directly informed their decision to build Kimi K2 with a massive 50% more experts in its total pool compared to another leading open-source MOE model, DeepSeek v3. They made a calculated bet based on their scaling law data that having a larger, more specialized bench leads to better overall performance, even if only a select few experts are called upon for any given play.
That's incredibly insightful. It's like discovering that even if a hospital only needs a small team of specialists for a particular surgery, having access to a much larger, more diverse roster of specialists on call across the entire hospital system still leads to better patient outcomes overall.
That's a great analogy.
But okay, there was another critical architectural trade-off they made, wasn't there? One that really highlights their dedication to this doer philosophy, the number of attention heads.
Ah, yes, the attention mechanism. Crucial.
Kimi K2 uses 64 attention heads, whereas DeepSeek v3, for comparison, uses 128. Now, on the surface, if you're not deep into the weeds of AI architecture, more sounds intuitively better, doesn't it? You'd naturally think 128 heads would give the model a richer, more nuanced understanding of the relationships within the data it's processing.
You absolutely would. That's a very common and perfectly logical assumption. More attention should mean better understanding, right?
Right.
However, the Kimi team's own rigorous experiments, which they detail in the report, revealed a surprising truth that really challenged this intuition. They found that doubling the number of attention heads, going from their chosen 64 up to 128, yielded only a tiny, almost negligible marginal improvement in overall performance on their evaluation test. We're talking less than a 1.2% gain.
Less than 1.2%. That's
Yeah.
barely anything.
Exactly. But here's the critical part. The cost of achieving that tiny gain was enormous. It came with a massive 83% increase in the computational load, particularly when the model was dealing with long sequences of text or code.
An 83% increase in compute cost for a 1% gain in performance. Wow.
Yeah. And this is precisely where the practical application, the doer philosophy, really starts to bite.
Because doers, agentic models, they inherently need to handle long contexts, right? That's their bread and butter.
Absolutely. An agentic model, a doer as we're calling it, it lives and breathes long context. For it to function effectively, it constantly needs to be able to read and comprehend entire documents, potentially thousands of pages long. It needs to process vast code repositories for complex debugging or refactoring tasks. It needs to remember and accurately utilize information gathered from long, multi-turn conversations it might have with various tools or APIs it's interacting with.
So that computational cost for long sequences becomes a huge factor.
It becomes a critical bottleneck, sacrificing a huge amount of computational efficiency, that 83% increase in cost for such a negligible performance bump, especially in the various scenarios where their agent needs to excel. That would have been an absolutely terrible trade-off for their primary goal, which was building a pragmatic, efficient, and cost-effective agent.
So choosing 64 heads was a deliberate sacrifice of a tiny bit of theoretical performance for a huge gain in practical efficiency.
Precisely. It was a deliberate, pragmatic, engineering-led decision. It allowed them to optimize Kimi K2 for what matters most in a real-world agent: practical usability, responsiveness, throughput, and overall efficiency, especially in those crucial long-context scenarios where these agents are expected to operate most of the time. It's really a testament to their unwavering focus on utility over chasing theoretical maximums on benchmarks.
Okay, when you lay it out like that, the strategy is crystal clear. Every single architectural choice, the number of experts, the sparsity of the attention heads, and it all seems to flow directly and logically from their core philosophy of building a practical, autonomous agent. Let's just put it all together for our listeners, maybe with a direct comparison again to DeepSeek V3, which is a great reference point for a powerful, modern MoE model.
Good idea. The contrast is revealing.
So compared to DeepSeek V3, Kimi K2 has 54% more total parameters, that massive underlying knowledge base. But surprisingly, it activates 13% fewer parameters for any given task, making it more computationally efficient at runtime.
Right. Bigger library, smaller working group.
And it has 50% more experts in its overall pool, thanks to that sparsity scaling law insight. But intentionally, it has 50% fewer attention heads to optimize for long context efficiency.
It's a beautifully consistent design philosophy, isn't it? It's not about just being bigger or more complex for its own sake. It's about being fundamentally smarter in how it allocates its resources and being ruthlessly optimized for its specific mission.
They've clearly engineered it from the ground up to be a highly efficient doer, not just another powerful thinker in abstract terms.
That's a fundamentally different goal, and as we've seen, it requires fundamentally different, sometimes counterintuitive engineering choices.
Okay, so we have this brilliant architectural blueprint meticulously designed for action, for doing. Now comes the truly monumental task, actually bringing this beast to life through training. We mentioned the scale earlier, pre-training Kimi K2 on an astonishing 15.5 trillion tokens of data.
Trillion with a T. It's hard to even comprehend that scale.
It really is. To try and put that in perspective for you, our listener, that's roughly equivalent to reading the entire English Wikipedia database over 4,500 times.
Wow.
Running a training process of this sheer magnitude isn't just about having enough data and enough supercomputers. It's an unparalleled engineering feat where stability is absolutely everything. One major hiccup, one single loss spike, which is where the model's internal learning process basically goes haywire, can corrupt weeks of progress.
And potentially cost millions of dollars in wasted compute resources. It can literally derail the entire project. It's an incredibly high-stakes game at this scale.
And this is precisely where the Kimi team introduced what is arguably the single most important technical innovation detailed in their report, something they call the MuonClip Optimizer.
MuonClip, yes. This is really clever stuff.
So to truly grasp why this is such a significant breakthrough, we kind of need to understand a fundamental tension, a trade-off that exists when you're trying to train these colossal AI models, right?
Exactly. There's always a balancing act. On one hand, you have optimizers like Adam W. Think of Adam W. as the reliable, steady Toyota Camry of AI optimizers.
Okay, the dependable choice.
It's incredibly stable. It will reliably get your model trained, get you to your destination eventually, but it's not always the absolute most efficient or the fastest way to get there. It tends to take its time, computationally speaking. It needs more data, more steps to reach peak performance.
So a solid workhorse, but maybe not a lightning-fast racehorse.
Exactly. Then, on the other hand, you have optimizers like Muon. Muon is much more like a high-performance Formula One race car.
Okay, sounds good. Faster is better, right?
Well, yes and no. Muon has been empirically shown in smaller scale experiments to be significantly more token efficient. That means it learns faster, it extracts more knowledge from each piece of data it sees, making more progress with less computational effort overall. Sounds great.
But there's a catch.
There's a big catch. Muon has this notorious, really nasty habit of becoming incredibly unstable when you try to scale it up to the immense size required for models like Kimi K2, especially within the complex Mo architecture. It's prone to what are known as exploding gradients or unstable updates, which lead directly to those catastrophic loss spikes we just talked about.
So the race car keeps spinning out of control and crashing.
That's a perfect analogy. It can just completely fly off the rails. The report specifically mentions the problem of exploding attention logits. Can you maybe unpack what that technical term means? Because it sounds pretty dramatic. It is dramatic when it happens. In simple terms, exploding attention logits refers to a situation where certain critical internal values within the model's attention mechanism, the part that's crucial for it to focus on relevant bits of the input data and learn relationships, they start to grow uncontrollably large, almost exponentially.
Like a runaway feedback loop.
Exactly like that. It spirals into numerical chaos. When these logit values explode, it causes the model's overall training loss, a measure of how poorly it's performing, to suddenly spike dramatically upwards instead of steadily decreasing. And that spike can completely derail or even permanently corrupt the entire training process, rendering potentially weeks or months of computation completely useless.
Ouch. So the monumental challenge for the Kimi team was clear. How do you somehow harness the incredible speed and token efficiency of the Muon race car without suffering those catastrophic project-killing crashes?
And MuonClip is their truly brilliant answer to that dilemma.
How does it work?
MuonClip is a really sophisticated hybrid solution. It cleverly combines the high-efficiency core of the Muon Optimizer with an ingenious safety mechanism they developed called QK-Clip. The real elegance of the solution lies in its incredible precision and minimal invasiveness.
Okay.
It acts like a very precise, almost surgical regulator. Throughout the entire training process, it continuously monitors those critical attention logit values, those internal numbers, in each of the 64 attention heads independently. Think of it as having a tiny dedicated sensor constantly watching each of those 64 focus points within the model's brain.
So it's monitoring each head separately.
Separately and continuously. Now, if it detects that the logit value in any single head is about to exceed a predefined safety threshold, indicating it's starting to explode, MuonClip activates only for that specific problematic head.
Not for the whole model.
No, just for that one head. It then gently, subtly rescales the internal weights just for that one isolated head, bringing its values back down into a safe, controlled range before they can cause chaos.
So it's not like a heavy-handed governor on the entire engine, slowing everything down just because one part is misbehaving. It's much more like having 64 tiny, intelligent circuit breakers, right? One for each tension head.
That's a fantastic analogy. That's exactly what it's like.
And they only trip when absolutely necessary and only for the specific component that needs it without disrupting the overall power flow or learning process elsewhere.
Precisely. And the crucial part about MuonClip's operation, the real genius, is its timing. It doesn't actually interfere with the main learning step itself. It allows the primary gradient updates from Muon, which is how the model actually learns and improves, to proceed as normal, maximizing efficiency. Instead, it uses the logit values as a diagnostic tool after each learning step. It looks at the state and makes these tiny corrective adjustments proactively, preparing the model for the next step, ensuring stability going forward.
Wow. So if I'm understanding this right, they've basically built a system that learns incredibly fast, leveraging Muon's efficiency. But it also simultaneously prevents itself from crashing by constantly self-regulating at the very fine-grained level. That allows them to train at a scale and with a speed that might have been completely impossible, just far too risky before. Right?
It's genuinely transformative for large-scale training. The result, which they proudly display in the training graph within their report, is frankly a thing of absolute beauty if you're into deep learning engineering. It's a perfectly smooth, consistently downward sloping loss curve, indicating stable, continuous, efficient learning. And the headline achievement. They achieve zero, absolutely zero major loss spikes over the entire 15.5 trillion token training run.
Zero spikes over 15.5 trillion tokens.
Zero. For a model of this unprecedented scale and complexity, using an optimizer known for instability, That is an absolutely phenomenal engineering achievement. MuonClip has effectively solved a critical, long-standing trade-off in large model training. It allows them to get the efficiency benefits of Muon without succumbing to its inherent instability at scale.
And the implications. That's huge for the whole field, isn't it?
Oh, think about what this means. It could fundamentally unlock the ability for researchers and companies everywhere to train even larger, more powerful models with unprecedented stability and maybe even faster. It could accelerate discoveries across the board in AI. This isn't just some internal engineering footnote. It feels like a foundational step forward for the next generation of AI development.
But, okay, even the best optimizer in the world, no matter how revolutionary and stable, is ultimately useless without high-quality fuel. And for an AI model like Kimi K2, that fuel is the data it's trained on. So the next big question becomes, how do they handle their data strategy? Especially in an era where, as we know, many people in the AI community are openly talking about hitting the limits, maybe even running out, of truly unique, high-quality, human-generated data available on the public internet.
That's a huge bottleneck.
You can't just keep repeating your existing data sets over and over again, right? Doing that leads to rapidly diminishing returns, and worse, it risks the model simply memorizing the data patterns rather than truly learning the underlying concepts.
That's a critical challenge facing the entire industry right now, and the Kimi team tackled it with a really clever synthetic data pipeline, specifically based on a technique they call rephrasing.
Rephrasing, how does that work?
For their most valuable, high-quality knowledge corpora, particularly in complex, fact-dense fields like mathematics or scientific literature, instead of simply feeding the exact same text passages to the model multiple times during training, they employed other powerful LLMs, ironically, to rewrite and rephrase the existing content.
Using AI to make better training data for AI.
Exactly. They had these LLMs rewrite the core information from various different perspectives, using different linguistic styles, changing sentence structures, maybe even altering the narrative voice. They even went so far as to translate complex math documents from other languages into English, just to increase the overall diversity and richness of how the same core concepts were presented in the final training dataset.
That is such an intelligent approach. It's essentially a way to squeeze more unique learning value out of their absolute best, most trusted data without actually needing entirely new, raw, human-generated data, which we know is becoming a scarce resource.
Precisely. By presenting the same underlying concepts, the same fundamental ideas, through multiple different linguistic and stylistic variations, the model is effectively forced to grapple with the core meaning. It has to learn the underlying principles and ideas from multiple angles, rather than just superficially memorizing specific phrases, sentences, or factual presentations.
It encourages deeper understanding, not just pattern matching.
Exactly. It's like trying to understand a complex historical event. You gain a much richer, more multifaceted understanding if you read about it as described by a dry academic historian, than by an engaging journalist, and maybe even through the eyes of a character in a historical novel. Each perspective adds a layer.
Yeah, that makes perfect sense.
And the Kimi report explicitly shows the results. Training on this carefully rephrased synthetic data significantly outperforms simply repeating the raw original data multiple times, especially on key question answering and reasoning benchmarks. It's a powerful testament to the fact that at this immense scale, it's not just about the quantity of data anymore. The quality, the diversity, and utility of every single token you feed into the training process truly, truly matter. It shows that intelligent data augmentation can be just as impactful, maybe even more impactful than simply finding more raw data.
Okay, so the monumental pre-training is finally complete. We now have this incredibly powerful, deeply knowledgeable base model. But right now, as you said, it's maybe akin to a brilliant, vast library or a comprehensive encyclopedia. It holds enormous amounts of information, potentially trillions of facts and relationships. But it doesn't inherently know how to interact with the messy, dynamic, real world. It doesn't know how to effectively use tools to achieve goals. It's like a repository of immense latent potential, but that potential hasn't really been unlocked yet for practical application.
It's smart, but not yet capable in an active sense.
Exactly. The crucial process of transforming that raw potential into a truly capable, aligned, and useful agent happens in the post-training phase. And from what their report details, Kimi K2's post-training process seems like one of the most sophisticated and deliberately agent-focused approaches I've ever come across. Could you walk us through how they actually bridge that gap between knowing and doing?
It truly is a masterclass in what they call agentic alignment. It kicks off with a phase called supervised fine-tuning, or SFT. Now, SFT itself is a fairly standard procedure in modern AI training. You basically show the model examples of desired input-output behavior.
Okay.
However, what sets Kimi K2's SFT phase dramatically apart is the nature of the data they use. It is anything but standard. The absolute centerpiece of their entire post-training strategy is something they call a large-scale agentic data synthesis pipeline.
Agentic data synthesis. That sounds important.
It's their innovative solution to what has been a massive bottleneck in training truly autonomous agents. The fundamental lack of readily available, high-quality examples of computers successfully using complex tools to achieve multi-step goals in the real world. We simply don't have enough human-generated data demonstrating sophisticated, error-free, multi-tool usage by AI, mainly because this kind of advanced capability is so incredibly new.
So they essentially had to create that crucial training data themselves, but presumably in a highly intelligent and scalable way.
Exactly right. They couldn't just hire thousands of humans to demonstrate perfect tool use over millions of scenarios. So they built what amounts to a massive, incredibly sophisticated simulation engine. Its sole purpose is to generate these complex, successful tool use examples at scale. The report describes it beautifully, I think, as a large-scale rejection sampling engine for behavior.
Rejection sampling for behavior. Okay, that's evocative. How does it actually work?
It's a multi-stage process. First, they meticulously assembled a truly enormous library of potential tools for the agent to use. This included adapting over 3,000 real-world tools, things like APIs for booking flights, searching academic databases, interacting with web browsers, controlling smart home devices, which they scraped and adapted from across the internet.
3,000 real tools is already a lot.
It is. But on top of that, to ensure an even vaster diversity of functional capabilities for the agent to learn from, they created another 20,000 synthetic tools simulating all sorts of potential functions and interactions.
Wow. Okay, so a massive toolbox. Then what?
Then they started throwing problems at the agent, almost like giving it an endless series of challenging virtual internships. They generate thousands upon thousands of different agent personas, each with unique goals, characteristics, and maybe constraints. Then they assign these personas complex tasks to solve using this massive library of tools.
And the agent just tries to solve them.
The agent attempts to solve the task. It makes a series of tool calls, trying different approaches, sequencing actions, maybe calling one tool, getting a result, calling another based on that result, sometimes having to backtrack and correct itself. A sophisticated simulator then provides realistic feedback for each step along the way. Sometimes the tool call works perfectly, sometimes it fails, sometimes it returns an obscure error message, just like using real software or APIs in the real world. It's designed to be a messy, iterative, and incredibly realistic simulation of trial and error.
Okay, so it's trying and failing and sometimes succeeding within this simulation. And then comes the rejection sampling part you mentioned earlier. That sounds like where the quality control, the gold standard, comes in.
Yes, exactly. This is the crucial filtering step. An independent, highly capable AI judge, likely another powerful LLM fine-tuned for evaluation, meticulously watches and evaluates this entire interaction, the whole sequence of actions the agent took, what they call a trajectory, from the initial prompt right through to the final outcome.
And it judges based on success.
It assesses the agent's performance against a predefined success rubric. Did the agent actually solve the problem it was given effectively and efficiently? Did it use the available tools correctly? Did it avoid unnecessary steps? Did it ultimately reach the stated goal? If the entire attempt, the whole trajectory of tool calls and internal reasoning steps, was deemed successful according to the strict rubric, they keep that entire successful trajectory. They add it to the special fine-tuning data set.
And if it failed?
If it failed, if it got stuck in a loop, if it used a tool incorrectly, if it simply ran out of allowed steps or failed to achieve the goal, they simply throw that entire failed attempt away, discarded.
So they might simulate millions of attempts just to get the successful ones.
Precisely. They might simulate millions upon millions of attempted solutions just to generate, say, hundreds of thousands or maybe even millions of perfect, successful examples of complex agentic behavior. It's an incredibly clever and highly scalable way to create a gold standard data set of what good looks like for complex agentic tasks, achieving a scale and quality that would be absolutely impossible, or at least prohibitively expensive, for humans to create manually. It's like having an infinite army of highly skilled human supervisors meticulously watching every single attempt and only saving the perfect demonstrations for the model to learn from.
Okay, after this incredibly rigorous supervised fine-tuning phase, where the model essentially learns by imitating these perfect successful trajectories, it then moves on to the reinforcement learning, or RL phase. This is for further refinement, right? To hone its abilities and really align its behavior with desired outcomes. And here again, the Kimi team seems to implement a really clever kind of dual-pronged approach that addresses both objective and subjective aspects of performance. How do these two prongs work together?
That's right. The RL phase is critical for fine-tuning beyond just imitation. And their dual approach is very smart. For tasks where there's a clear, unambiguous, objectively verifiable right or wrong answer, they utilize a system they call the Verifiable Rewards Gym, or RLVR.
Verifiable rewards.
Yes.
Sounds straightforward.
It is, and that's its strength. Think about it like this. For mathematical problems, the reward signal is incredibly simple. Did the model arrive at the correct numerical answer? Yes or no? Binary. For coding tasks, the reward is even more definitive and robust. Does the code the model generated successfully compile without errors? And does it pass all the predefined unit tests designed to check its functionality?
Okay, so grounded in objective reality.
Absolutely. This approach grounds a huge fundamental part of the model's learning process in objective, undeniable success. There's no ambiguity, no room for interpretation, no shades of gray. It either achieved the verifiable outcome or it didn't. This ensures a rock-solid foundation of competence and reliability in domains where success can be quantitatively measured and clearly observed.
But what about all the other tasks, the more subjective ones? Things like write a truly creative and engaging short story. Or is this response genuinely helpful and empathetic, not just technically correct? There's no simple unit test you can run for creativity or helpfulness. Traditionally, this is where most reinforcement learning from human feedback, or RLHF, processes rely heavily on incredibly expensive and time-consuming feedback from actual humans. How did Kimi K2 handle that subjective alignment challenge, apparently without needing a massive army of human labelers?
This is where their second RL prong comes in, a mechanism they call self-critique rubric reward, and it's remarkably innovative and potentially much more scalable. The core idea is this. The model itself, when faced with a subjective prompt like write a story or explain this complex topic clearly, first generates multiple different possible responses.
Okay, generates options.
Then it acts as its own internal judge. It compares these various responses against each other and ranks them. But crucially, it doesn't rank them arbitrarily. It does this based on a predefined set of internal principles, or rubric, that it has been carefully trained on during the earlier SFT phase principles like ensuring clarity, maintaining relevance to the prompt, maximizing coherence, and importantly, actively avoiding undesirable traits like sycophantic behavior, just telling the user what it thinks they want to hear, or generating unnecessarily verbose, rambling responses.
So it essentially becomes its own quality control system for these subjective tasks using principles it learned.
Exactly. It learns to prefer responses that align with these desirable qualities.
Now, the immediate red flag, the big question that probably pops up for me, and I'm sure for many listeners as well, is this. Okay, but won't the model just end up reinforcing its own bad habits or existing biases if it's the one judging itself?
Yeah.
Couldn't it easily get stuck in some kind of echo chamber or feedback loop of its own making, essentially congratulating itself even for mediocre or flawed output? That seems like a legitimate and quite serious concern when you give an AI the power to self-critique without external human oversight.
That is indeed the crucial question, the potential Achilles heel of any self-critique system. And this is where the final, truly brilliant piece of their post-training puzzle, something they call closed-loop critic refinement, comes into play. This is, in my personal opinion, one of the most ingenious aspects of their entire training pipeline, because it directly addresses that drift problem.
Closed-loop critic refinement. Okay, how does that prevent the echo chamber?
Here's the clever part. They take the critic, which is the internal part of the model responsible for doing that self-judging and ranking based on the subjective rubric, and they continuously fine-tune the critic itself. But crucially, they fine-tune this subjective critic using the performance data generated from the objective, verifiable tasks in the RLVR gym that we just discussed.
Wait, so the model's proven ability to objectively get things right, like passing coding tests or solving math problems, is used to make it a better judge of subjective qualities like creativity or helpfulness. That sounds almost paradoxical, but utterly fascinating if it works.
Exactly. Think of it like this. The model's undeniable objective success at verifiable tasks, like successfully passing a rigorous unit test suite for a piece of generated code or correctly solving a complex multi-step math problem, is not just used to directly improve its problem-solving abilities in those domains. That verifiable success, that signal of objective correctness, is also distilled and transferred into its evaluation faculty, its internal subjective critic.
It learns what good looks like objectively and applies that standard internally.
Precisely. This process rigorously grounds the subjective critic in objective reality. It prevents the critic from drifting away from useful grounded judgments or reinforcing its own potentially flawed biases when evaluating subjective outputs like stories or explanations. It's almost like teaching a subjective art critic about the fundamental principles of engineering or physics. It grounds their aesthetic judgment in a deeper, more objective understanding of how things are actually built and how they function correctly.
Wow, that is a powerful concept. It's a scalable way to align the model with complex, nuanced human preferences without needing that constant, expensive stream of human labelers for every single step of the reinforcement learning process. It's a closed-loop system that continuously self-corrects and improves its own internal sense of quality, anchored by objective success.
It's a really elegant solution to a very hard problem in AI alignment.
Okay, the philosophy behind Kimi K2 is clearly ambitious. The architecture is undeniably clever. The training process, especially with MuonClip, is incredibly innovative. And this post-training refinement, particularly that closed-loop critic mechanism, is truly ingenious. But the big question remains, does all of this meticulous design, all this complex engineering, actually add up to superior real-world performance? Let's finally get to the bottom line, the benchmarks. The Kimi K2 report provides an absolutely exhaustive performance analysis, comparing it head-to-head against the best of the best, both the leading open-source models out there and, crucially, the top-tier proprietary closed-source models like OpenAI's GPT-4.1 and Anthropic's Claude Opus 4. Here's where it gets really interesting. What were the initial impressions? How did it stack up, especially on the agentic tasks Kimi K2 was explicitly built to excel at?
The results are, quite frankly, remarkable, especially, and it's worth repeating this, when you constantly keep in mind that Kimi K2 is an open weight model, meaning its core weights are freely available, downloadable, and modifiable by anyone, unlike the proprietary giants.
Okay, so how did it do?
Let's start exactly where Kimi K2 was designed to shine. Agentic tasks, the doing part. In agentic coding, for instance, which tests a model's ability to actually solve real-world software bugs scraped from GitHub issues, or write functional code from scratch based on complex specifications. Kimi K2 isn't just a leader among open-source models, it's significantly closing the gap, and in some cases even surpassing the top closed-source giants on key benchmarks like SWE Bench Verified.
Beating proprietary models on coding tasks.
On SWE Bench Verified, the Instruct version Kimi K2 Instruct scores 65.8%, which blows away other open-source models and puts it well within striking distance of the leaders. And on competitive coding benchmarks like Live Code Bench, it actually leads all models, open and closed, with a score of 53.7%, where competitors are generally in the mid-40s.
Wow, that's not just incremental improvement, that's leadership.
It's a direct, unequivocal validation of its doer design philosophy and that intensive agentic training process we discussed. It shows it genuinely excels at practical, real-world coding challenges that require not just understanding the request, but actual multi-step problem-solving, tool use like running code, debugging, and execution. That's a huge leap forward for open source capability in this critical area.
That really is a massive win for the entire open source community, isn't it? It strongly suggests that you don't necessarily need a closed, multi-billion-dollar corporate budget to compete at the absolute highest levels of agentic capability anymore.
Exactly. And the same compelling story holds true when you look at agentic tool use. On benchmarks like Tau2 Bench and Ace Bench, which are specifically designed to meticulously measure a model's ability to orchestrate complex, multi-turn sequences of tool usage to achieve specific goals, tasks that inherently involve planning, making multiple API calls, interpreting the results correctly, handling errors gracefully, and self-correcting along the way.
The core agentic loop.
Precisely. Kimi K2 is, again, right at the very top of the leaderboard, competing fiercely with, and often outperforming, the best proprietary models. This clearly demonstrates that their innovative agentic data synthesis pipeline and that sophisticated dual-pronged reinforcement learning process really paid off precisely where they intended them to. They built it to do, and the benchmarks show definitively that it does.
But what's perhaps even more impressive to me looking through the results is that this deep specialization and optimization for agentic tasks doesn't seem to come at the cost of it being a strong generalist. In fact, Kimi K2 holds its own, and often excels, across a surprisingly wide range of general AI capabilities.
That's a really important point. It's not a one-trick pony.
Not at all. In really demanding math and STEM benchmarks, for instance, tests like AMY or GPQA Diamond, which probe advanced reasoning and complex quantitative problem-solving skills, it's highly competitive. It frequently leads the entire open-source field and stands shoulder to shoulder with the top proprietary models.
So it can reason deeply as well.
It seems so. And on broad general capabilities, like instruction following, measured by benchmarks like IFEVL, which test how well a model understands and adheres to complex, nuanced, multi-step instructions. Kimi K2 actually leads all models, both open and closed source.
Leads everything in following instructions. That's huge for usability.
It really is. So what we're looking at here isn't just some niche specialist that's only good at coding or using tools. It appears to be a highly capable specialist built on the foundation of a top-tier generalist brain. It seems capable across the board, which makes its agentic skills even more impressive.
And beyond all these static, often academic benchmarks, we also have the increasingly powerful court of public opinion, right? We're talking about the LMSYS chatbot arena.
Ah, yes, the blind head-to-head user voting.
Exactly. Where thousands upon thousands of real users blindly vote on the outputs of two anonymous models, giving us a noisy but valuable real-world gauge of perceived usefulness, helpfulness, and overall quality in practical interactions. As of the time the report was released, around mid-July 2025, Kimi K2 Instruct was ranked as the undisputed #1 open source model.
#1 open source is great, but how did it compare overall?
Astonishingly well. It was ranked #5 overall, placing it firmly among the very best, most preferred proprietary models in the entire world, according to this large user base.
5th overall, judged by real users. That's incredible for an open-weight model.
It's an incredibly powerful signal. It tells us that this model isn't just a benchmark king that performs well on contrived tests on paper. It's genuinely useful, perceived as highly capable, and produces high-quality, practical responses in the wild across a huge diversity of real user demands and prompts. It indicates a level of practical utility and user satisfaction that truly resonates with everyday users, not just AI researchers.
Okay, benchmarks are one crucial piece of evidence, and that public opinion from the arena strongly validates them. But the real acid test, especially for you, our listener, trying to understand the potential impact, is what a model like this can actually do in practice. Can it really handle those complex, multi-step agentic workflows? And the documented use cases provided for Kimi K2 really seem to exemplify the kind of sophisticated agentic workflows the creators dreamed of enabling.
They shared some pretty compelling examples.
They really did. There's a fantastic one where they tasked Kimi K2 with planning an entire concert tour for a hypothetical band. And this wasn't just, generating a list of suggested cities or venues. It involved the model autonomously making 17 distinct sequential tool calls.
17 calls, like
Yes, things like interacting with flight booking APIs to find suitable travel options, using other tools to find and evaluate restaurants near venues, automatically updating calendar entries with confirmed dates and times, managing hotel reservations, all executed in one incredibly seamless, apparently autonomous session. It took the high-level, planned this tour, and executed the entire complex multi-step process involving multiple external tools.
That perfectly highlights its ability to actually chain together multiple actions, using different tools, interpreting the results, and proceeding logically to achieve a complex, high-level goal. That is the very definition of true agentic behavior. It's not just a single-shot query and response. It's sustained, goal-directed action.
Exactly. And there's another really compelling example they shared, where Kimi K2 was tasked with analyzing a dataset containing salary information. Again, it didn't just write a simple summary of the data trends. It initiated a sophisticated 16-step workflow.
16 steps for data analysis. What did that involve?
It included things like invoking a code interpreter tool to perform complex statistical analysis directly on the raw data files. It then went on to generate multiple different types of charts and visualizations based on that analysis, presumably choosing appropriate chart types for the data.
So it's analyzing and visualizing.
But here's the kicker. It didn't just describe the charts it made. It actually assembled everything, the analysis findings, the generated charts, maybe some explanatory text, into a final interactive HTML dashboard file, complete with apparently clickable elements and dynamic displays. It delivered a finished product, a fully functional, usable data artifact, not just a text description of what it found or what someone should do.
That's the doer philosophy in action right there. Moving from mere information retrieval or generation to creating tangible, useful deliverables. That's a fundamentally different kind of output.
It really clarifies what an agentic AI is capable of achieving.
Of course, while the capabilities are stunning, no model is perfect, right? And it's always crucial, especially when considering using these powerful tools, to be clear-eyed and realistic about their limitations. The official report from Moonshot AI themselves is commendably transparent about this.
What limitations did they acknowledge?
They mentioned that Kimi K2 can sometimes get stuck in repetitive loops, particularly on very complex tasks. And it might occasionally generate far too many tokens, essentially becoming overly verbose or getting bogged down in an infinite process when faced with very hard, highly abstract reasoning problems where a clear path forward isn't obvious.
Okay, so potential for getting stuck or rambling on hard problems. What else?
Beyond their official acknowledgments, user reports and independent reviews have surfaced some other practical gotchas to be aware of. The API, while incredibly powerful and now very cheap, can sometimes be a bit slower in terms of response latency compared to some of its more established, highly optimized proprietary competitors. That might impact certain real-time or latency-sensitive applications.
Speed is often a factor.
And crucially, a significant limitation right now is that Kimi K2 currently lacks native multimodality. This means it cannot directly see or interpret visual information like images, charts, or diagrams, nor can it process or understand video content. It's primarily text-based in its current iteration. So you couldn't, for example, show it a complex graph and ask it to interpret the trends directly from the image.
That's a notable gap compared to some other leading models.
It is. An in-depth technical review also pointed out what they termed a systemic tool mismatch in some specific areas. Particularly, the model occasionally struggles with the exact syntax or required conventions for interacting reliably with file systems, reading, writing, navigating directories. This could create friction in certain automated workflows that heavily rely on precise file manipulation.
Good to know for developers building file-based automations.
And finally, the universal caveat that applies to absolutely all large language models today, Kimi K2 included, it is absolutely not immune to hallucination. It can still generate plausible sounding but factually incorrect or nonsensical information. So while it is incredibly powerful and remarkably capable, especially as a doer, it's definitely not infallible. Users need to remain aware of these edges, implement appropriate safeguards, and build workflows accordingly. Verification is still key.
All very important considerations for anyone looking to deploy or build applications on top of Kimi K2. But now let's talk about the final and arguably the most significant piece of this entire story, the one that has potentially profound disruptive implications for the entire AI industry landscape, the economic disruption that Kimi K2 represents. Here's where it gets really interesting.
This part definitely turned heads.
First, as we mentioned, Kimi K2 is being released as open-weight, published under a very permissive Apache 2.0 license. This means you, our listener, if you have the technical capability, can literally download the model weights, modify them if you wish, and run the model entirely on your own infrastructure. That grants immense freedom and control.
Huge for transparency and customization.
But it's their pricing for the hosted API access that is truly aggressive. I mean, jaw-droppingly aggressive. It feels like a move deliberately designed to fundamentally reshape the market dynamics for powerful AI models.
It's staggering, frankly, and it puts immense, almost unprecedented pressure on the established proprietary players. Let's try and put it in stark, concrete terms. To process 1 million output tokens, which, remember, is a very significant amount of generated text, may be roughly equivalent to processing the entire Harry Potter book series about 20 times over.
Okay, 1 million output tokens, how much?
Kimi K2's API costs approximately $2.50 for that volume. $2.50.
$2.50 for 1 million tokens. That sounds incredibly low.
It is. Now compare that directly to a top-tier proprietary model like Anthropic's Claude Opus 4. For the exact same amount of output tokens, 1 million Claude Opus 4 costs around $75.
$75 versus $2.50. Wait, that's a 30x price reduction? 30 times cheaper.
30 times. That's not a small difference. That is not an incremental improvement in cost effectiveness. That is a mind-boggling, potentially market-breaking price differential.
A 30x price reduction changes absolutely everything, doesn't it?
Yep.
That's not just making things a bit more affordable. That's a fundamental paradigm shift in the accessibility of state-of-the-art AI.
It's an absolute game changer for the entire AI ecosystem.
Right.
This pricing strategy radically, fundamentally democratizes access to cutting-edge agentic AI capabilities. Just think about what this enables. A small, bootstrap startup with a brilliant idea but very limited capital.
Or just a single independent developer working on a passion project in their spare time.
Or an academic research lab operating on a tight grant budget. They can now realistically build and deploy incredibly sophisticated autonomous systems using Kimi K2 on a budget that was utterly, completely unthinkable just a year, maybe even 6 months ago.
So if you've ever dreamt of building an AI application that could, say, automate large parts of your customer support workflow or handle complex data analysis pipelines autonomously, or maybe even run sophisticated adaptive marketing campaigns without constant human oversight.
The barrier to entry, the cost barrier, has just been dramatically, almost violently lowered. What was previously only feasible for giant tech corporations with massive cloud computing budgets is now potentially within reach for independent innovators, small businesses, researchers, basically, for you, the listener.
And the knock-on effects.
This isn't just about making existing AI applications cheaper. It puts immense, unprecedented competitive pressure on all the proprietary players in the market. They now have to compete not just on raw capability or benchmark scores, but on extreme cost effectiveness as well. They can't just rely on being slightly better if they're 30 times more expensive.
It forces their hand on pricing.
It absolutely does, and this kind of radical cost disruption, especially when combined with the simultaneous open-weight release of the model itself, is precisely the kind of catalyst that fuels a Cambrian explosion of innovation, particularly within the vibrant open-source AI community. It makes advanced AI accessible to orders of magnitude more people, which inevitably leads to a massive surge of creativity, experimentation, and new application development.
So to try and bring this all together, pull out the core insights for you to take away from this deep dive today. So what does this all mean? Kimi K2 really does feel like a landmark release in the ongoing evolution of artificial intelligence.
It feels pivotal.
It serves as a powerful validation of that era of experience concept we discussed, proving it's not just a theoretical idea, but a practical, effective training paradigm for building truly capable, action-oriented agents. And perhaps most importantly for the broader ecosystem, it definitively proves that open-weight models can achieve state-of-the-art, even world-leading performance in the critical and rapidly emerging domain of agentic intelligence. And crucially, they can do so at a dramatically disruptively lower cost.
And it's crucial to really understand Kimi K2's specific position in the market. It isn't necessarily trying to be the absolute best thinker on every single abstract reasoning benchmark or the most verbose and engaging conversationalist out there. That wasn't its primary design goal. Instead, it has firmly, undeniably established itself as arguably the most capable and the most accessible agentic doer currently available in the entire open source world.
And the implications vary depending on who you are, right?
Absolutely.
Yeah.
For developers and startups listening to this feels like a clear green light, a signal that the barrier to entry for building genuinely autonomous applications, things that were maybe just sci-fi a couple of years ago, has just been dramatically lowered. Go build. For researchers, the open-weight base model is an absolutely fantastic new artifact. It's a powerful new tool to experiment with, to probe its capabilities and limitations, and potentially to build upon for future innovations in agentic AI. And for enterprise leaders, it presents a fascinating, potentially highly cost-effective new strategic option for driving automation, efficiency, and maybe even entirely new business processes that simply weren't economically viable before.
Indeed. I even saw one user review suggesting a really powerful hybrid approach that could be incredibly impactful for businesses and maybe even individuals looking to maximize productivity.
Oh, what was the hybrid idea?
The suggestion was, use the highly resilient and incredibly cheap Kimi K2 for the heavy lifting, the grunt work. Things like initial information gathering across multiple sources, executing complex multi-step tasks involving multiple tool calls, generating first drafts of code or documents, or even managing entire automated workflows from start to finish.
Okay, use Kimi K2 for the doing.
Exactly. Then you could potentially take its comprehensive output, the collected data, the executed actions, the generated draft, and pass that refined output to a more expensive, perhaps more reasoning-focused proprietary model, like a GPT-4 or Claude Opus, specifically for that final layer of deep analysis, nuanced insight generation, strategic interpretation, or critical review.
Ah, I see. Like using Kimi K2 as the incredibly efficient engine, and maybe a more expensive model as the sophisticated final editor or strategist.
Precisely. This kind of combined approach, leveraging the strengths of each model type, strategically Kimi's low-cost execution power, and another model's potential reasoning depth, could be a powerful recipe for unlocking truly massive productivity gains across many industries, all while maintaining an optimized blended cost structure. It's about using the right tool for the right part of the job.
That's a very smart workflow. And thinking about these possibilities, this raises an important question for you, our listener, as we wrap up. Kimi K2, with its capabilities and especially its economics, has fundamentally thrown down the gauntlet in the AI world. It has provided both a detailed technical blueprint and a compelling new performance benchmark for the very next wave of AI development. It undeniably accelerates the ongoing, perhaps inevitable, industry shift away from passive chatbots that simply respond to queries towards active, goal-oriented agents that can autonomously plan, act, and achieve complex objectives. The era of the Doer AI certainly feels like it's truly here, or at the very least, rapidly dawning and well and truly on its way.
So the final thought to leave you with is this. Given this newfound level of accessibility, this proven agentic capability, and this dramatically lower cost point, what previously impossible autonomous tasks, what currently human-driven workflows, or what entirely new applications will you now seriously consider building, automating, or leveraging in your own work, your own business, or even your personal interests? The possibilities just got a lot broader.
A question worth pondering.
And that is all the time we have for today on the Deep Dive. Huge thank you for tuning in to our exploration of Kimi K2.
We really hope it gave you a clearer picture of what feels like a genuinely pivotal moment in the AI landscape. Join us next time as we continue to explore the cutting edge of technology and its impact. Until then.